Hi. I'm currently a ML engineer at Noonam. So Noonam is a battery health analytics platform. So we deploy models and understand the security risks and as well as health analytics for the lithium ion batteries. It can be running on regular EVs. It can be running on two or three wheelers or even large energy storage systems. So due to the nature of the deployments that is in this scenario, so we had to take care of think about deploying the models on the edge to provide the inferencing faster, quicker, and to also address the issues of the critical security related inferences. So there is quite a things that I learned while running neural networks on an microcontroller or even neural accelerators. So just to start get things started, uh, first thing that comes to mind that is when to deploy on the edge, or when to deploy when the edge is mentioned here is that edge is, it can be on a mobile system like Android and iOS. It can be on microcontroller, it can be on Raspberry Pi, or even neural accelerator chips. So the four things that drives everything to the for the decision is uh, mentioned in the slide. So starting from first to uh, first to fourth. So in reduced priority. So if the system has to be very low latency, like you have to do inferencing very quick, and the response time has to be very low, then this is the most useful and most ideal scenario to deploy on the edge. Second is the privacy scenario, where you don't want the data to leave the source system or the user system, but also you have to provide the inferencing there as well. So running neural networks or running any kind of model there itself. So that is the two most biggest part of determining when to deploy on the edge. Fourth and sixth, third and fourth points are, it depends on the situation or depends on the environment of the deployment. So in some cases, the devices or the systems or in the deployment environments are quite network constraints. For say, in a rural environment where the network availability is not that much, so that in that case you have it would be easier, or it would be actually very user friendly if the networks or the inferencing happens on the edge, so that there is not too much to and fro from the central, from the server, from wherever it is running, AWS, GCP, or even Azure. So there's not that too much flow from the server to the on the actual edge, so that the user can get the information as quickly as possible without worrying about network constraints. Okay, you are waiting for or at least you are monitoring for some events or monitoring for some markers, and suddenly the network drops, or suddenly the speed of the network drops very drastically. So that is a very huge hindrance in critical situations where it is actually absolutely needed. And the fourth point is throughput. So for say, the number of inferencing you are doing per second is quite high. So in that case, it also makes sense to deploy the whole neural network or the whole inferencing engine there itself. If it's possible, do it there, or otherwise some part of hybrid inferencing should be there. So these are the four primary points to consider on to even start thinking about if the solution needs to be deployed on the edge or not. So considering that, considering the earlier slide that when to deploy, then the second part comes into is the type of deployment that can happen. So I mean, in normal scenarios, that you train the neural network with large amount of data and then you run inferencing on inferencing. So um, in that stage, there are multiple things that happen in normal MLOps scenarios, that you have to do continuous monitoring, you have to check for data drift, you have to do model refreshment if there is significant data drift observed. So in that scenario, two kinds of deployment can come into picture. One is the training also happens on the edge as well as the inferencing. So that is the bread and butter of the whole topics of federated learning. So since that would be a huge part, I'm just glancing over through it what it is and what are the use case, or what are the markers for that. So there always going to be a base model to start with. So the base model gets trained on the user data, which the data doesn't leave at all from the user devices at all. So the base model gets trained on the weights and biases gets updated, and in cases if it needed, the model gets, and the updated models with the weights and bias get shared. It can be shared with a centralized in normal scenarios, a centralized MLOps system, or it can be shared in other shared devices as well. So that is the in very crux run training at the edge and inferencing there itself. So one of the biggest advantages, the data never leaves. So the second point that was mentioned in the slide one, that uh, privacy scenario, what when to deploy on the edge, that is the biggest advantage of federated learning or training on the edge. So the user data never leaves the source system, and only the model gets trained on the specific data itself. So in contrast to a centralized model training and serving scenario, so each model each user data or each deployment devices gets trained differently, and each kind of model refreshment happens there itself, because at the end, if all the training happening is all happening on the edge, including the inferencing. And this also goes to very customized model deployment for specific set of users and specific segment of users as well. So just to glancing to the training at the edge, then comes in the inferencing at the edge. So here is this is the primary point of the whole talk itself, that when how what happens while doing the inferencing at the edge itself. So in this scenario, the uh, all the training, all the validation, everything happens in a centralized manner, like normally how model training happens. Only the inferencing happens on the edge. So the edge can be in the same scenario. Edge can be a mobile device, edge can be a neural accelerator, it can be edge TPUs as well, depending on the scenario, depending on the environment. So one of the biggest drawbacks is that it is it would, after the deployment, uh, the model update, depending on the scenario or the data, the model update or the model refreshment is quite difficult to do, because there is no amount of training happening on the edge. The only thing happening there is the inferencing. So all the training happens offline in a centralized scenario. So that is one of the biggest disadvantage while doing inferencing at the edge. And in both of the cases, the one biggest factor to determine even which neural network to use, what architecture to use, is the memory constraints in the term of the total memory usage, and even the total footprint of the model itself. So that brings part to the second part, which is how to reduce the model size itself, so that total model footprint gets reduced, and as well as memory usage also gets reduced. So that is where the model quantization part come into picture. So in normal scenarios, when the model gets trained, all the parameters, weights and biases, everything gets stored into 32-bit floating point precision format. But to store that amount, of to store all the weights and biases for each layer, for in a 32-bit floating point precision format, it will take a good amount of space if the idea is to run it on the edge, in can be microcontroller or a neural accelerators. So the point is to reduce the floating point precision from 32-bit to 16-bit or 8-bit integers. So so to do that, I mean, to actually go from 32-bit to 16-bit or 8-bit, the one of the biggest drawbacks is the loss of accuracy. How much accuracy is lost, how much latency is gained through that loss of accuracy, and the trade-off between them. So uh, while determining the trade-off, that how much accuracy, loss of accuracy is acceptable with the gain in latency, there's actually there is not that much accuracy loss uh, is evident while considering the gain in latency. So this is the attached references are in line with the TensorFlow Lite model optimization toolkit, where the model size gets almost reduced by 3 to 4 times with minimal loss of accuracy. Or in some cases where the almost all the layers are convolution layers, the loss is actually very negligible. uh, so while determining what kind of quantization to do, this plays a big picture, because the amount kind of quantization that is preferred on any of the process will determine that the trade-off between the accuracy loss and the latency gain. So there are primary two types of quantization currently in practice, or currently being deployed in current scenarios. So two part is the post training quantization, where all the quantization happens after the model is trained. So here the quantization is from by default, the floating point precision is 32-bit. From that to 16-bit floating point, and then 8-bit integer points, precision points. So depending on how much the precision point needs to be used, different libraries, different frameworks supports different types of hardwares for the scenario. For that scenario, in some cases, for say in TF Lite model optimization toolkits, uh, different kinds of post training quantization prefers either CPU, GPU, or HTPU, uh, or even microcontrollers in that scenario. So primarily, all the post training quantization is divided into uh, three primary post quantization methods. One is reducing from 32-bit to 16-bit floating point. Another is reducing from 32-bit to 8-bit floating point. Another is the dynamic range. So in all of the different types of quantizations, the accuracy loss is almost negligible while dealing with post training quantization with 16-bit floating point precision. So in that scenario, if it's suitable for CPU and GPU both, and for and the accuracy loss is almost negligible while considering the amount of latency gain, or the amount of memory footprint saved. So almost 4 times reduction in size of the model with very negligible amount of accuracy loss. That uh, level of accuracy loss goes slightly bit higher once the type of quantization goes up. So for say in dynamic range, that is the least among the rest, barring floating points, 16 of sorry, floating 16-bit floating point precision, and 8-bit integer precision gives the highest amount of accuracy loss among the three, although being the lowest amount of mm, producing almost 5 times reduction in model size. The accuracy loss is the highest here, because that is understandable, as the precision point comes from 32-bit to 8-bit integer systems. So the second part of quantization is quantization aware training. So in earlier scenario, the quantization happens after the model is trained, everything is in process, then the quantization happens. In quantization aware training, the quantization happens while the network is being trained itself. So in this scenario, it all boils down from 32-bit floating point to 8-bit integers with negligible loss in accuracy. So but the one of the primary drawbacks is that it is not supported in most of the edge hardwares, and on top of that a very small amount of um, very small set of neural networks actually is supported currently. So among the two types of quantization methods and the different quantization methods inside in subsection of them, the second part is that which one to choose and in what scenario. So the rule of thumb is, if the whole idea is to just reduce the size, simple post-training float 16 quantization would give almost for 3 to 4 times law reduction in memory size with negligible accuracy loss. So if the idea is to just reduce the size by half or even twice that amount, that would almost take all in almost all of the scenarios. Now if the loss of accuracy is the loss of accuracy is much more required, or in it is much more evident to reduce with gain in with reduction in model reduction in memory footprint of the model size, then post training dynamic range or post training 8-bit integer would be preferred choice. But in that scenario, the accuracy loss would be higher with gain in latency and with reduction in memory footprint. So there are always trade-off between which one to choose, and it will always depend on which one to prioritize. So in scenarios where the amount of model size is the reduction in model size is acceptable within the range, that in almost 80 to 90% scenarios, float simple post training 16-bit floating point precision quantization would work. So apart from model quantization itself, there are two primary or two very widely used methods of to reduce the size of the model. One of the major among them is weight sharing. So in weight sharing, all the weights of the individual layers are clustered into n number of are clustered into n number of clusters, and while sharing the weights, instead of sharing the actual weights, the centroids of each cluster in scenario n clusters would be shared. So in that scenario, it will almost reduce to almost 50% model size would be reduced, with again with the same amount of same amount of negligible loss in accuracy. So with just simple weight sharing itself, when there are multiple layers of multiple layers, and each layer's weight needs to be reduced quite significantly without losing much accuracy, and almost one and a half, at least 50% reduction in the model size itself, it would give the it would give the most easiest way to reduce model size. And this would happen again after the model is trained and everything is done. Before the deployment, this can be done easily. So the same way post training quantization happens, this is also happens while after the training is done. Another popular method, another useful and I think very widely used method is pruning, where the insignificant parameters is removed altogether while dealing with reduction in the model size. So so the whole point of deployment from training to from training to the edge hardware is just to reduce the amount of model size, the whole footprint of the model without losing much accuracy. So that trade-off will always comes down to which one to choose, which one to prioritize, and how the networks or how the types of neural networks are being chosen. So each choice in each cases, while choosing quantization to reduce the size, or choosing any other reduction method for say weight sharing or weight clustering, would yield different results and would be suitable for the scenarios that the model is being deployed. So how the each uh, microcontrollers, each HTPUs, or even popular neural accelerators perform, which different kind of neural networks which under different kinds of load. So the all the benchmarks, all the benchmarks are required, and the added papers is added in the benchmark section. Think with that, all the references are also added here. I think with that I can conclude the whole talk. Thank you. So I am reachable over LinkedIn, Twitter, and GitHub as well. I think this slide will also be shared with all of you.